we're going to take two things that you already know how to do, and we're going to apply them to parametrics. So the two things are optimizing. Can anybody give me a summary or a quick like Reader's Digest, like how do we optimize something, or what does that even mean in a calculus class? You've learned it before, you did it all last year and you did it again this year to optimize something. Go ahead, Rain.
So you find a max, like you make the derivative equal to max, something. I know we did that in the past, I don't know.
Yeah, you're using good words, you're using words like derivative, you're using words like max. Kaylin, you want to take a stab at it?
You take the derivative, set it equal to 0, and then find the max by, like, you find the zeros, and then you find where it changes, where the derivative changes, and then the max, and then you find use the max as you put it back into the equation and find where that.
Yeah, if we actually want to figure out the max, how do you know the difference between a max or a min using the way you're describing?
If it changes.
If it what?
The derivative changes from negative to positive, positive to negative.
Okay. And is setting it equal to 0 the only option?
Or is it 0 over 1? 1 over 0.
1 over 0, yeah, so to undefined. So optimizing is looking for derivative changes. Around critical points. So we already know how to do that in theory. We're just going to apply it to parametrics. Okay, the critical points we find by setting that derivative equal to both 0 and undefined. That gives you the critical points. And then you check to see what type of change is happening around the critical points, and then that is optimization. All right, the other thing that you know how to do is finding the length of a curve. All right, now that one is we did not do it last year in AB. You learned it last semester on your own. Does anybody remember how to find the length of a curve?
Is that we did this last semester?
Mm-hmm.
It's the integral of the function times the square root of 1 plus the derivative squared?
Oh yeah, you're definitely, so it's the integral of, yeah. So yeah, you're, okay, so this is just,
Just the square root of 1.
Okay, so just the integral of the square root of
1 plus the derivative of the function squared.
Okay, so I'm gonna, 1 plus the derivative squared, and then there was a dx out here, and then your integral goes from a to b to find how long is. Do you remember where the 1 comes from? Yeah, before it was 1, it was dx over dx, and that was squared. So that actually comes from the Pythagorean theorem. This is a squared. This is how you find the hypotenuse of a Pythagorean theorem. And a squared plus b squared equals c squared. Only we're not finding the hypotenuse of a big triangle. We're finding tiny baby hypotenae. I don't know if that's the hypotenuses, hypotenae, whatever the plural of that is. And then we're integrating it to add them all together. Now that we're in parametrics, what variable do we need to include now? T. Okay, so everything's not with respect to x anymore. Everything will be with respect to t. But you know, so the concept you know how to do. We're just going to apply it to something new. All right. Okay, so let's try finding the lowest point. Hey. So this is an optimization problem, so we are minimizing. When you're doing the lowest point, okay, what are we minimizing? If you're thinking, what coordinate do you want to find the smallest value for? If we're talking about lowest. Why? Parametrics separate thinking about left and right from thinking about up and down. And so if we want to find the lowest point, we are minimizing the y value. It has nothing to do with the x value. It has only to do with the y value. So that x value is arbitrary. It doesn't even impact what we're gonna do. We're only looking for the smallest possible y value within the parameter that we've been given. We also, one thing that we did learn a lot in AB, and then it just reinforces, you have to remember to check the endpoints. So not only do we have to find critical points, but we have to find our endpoints as well. So 2 things, check endpoints and check critical points. And that's how we optimize something. Well, let's check our endpoints first. So we want to find what the y endpoint would be with the parameter of -1. So that would be 2 times the secant of -1. And then we also want to find the endpoint at the parameter of +1. So that would be 2 times the secant of +1. All right, so in radian mode, so that's the other thing. If you're in AP Physics, you might be in degree mode. So please make sure, I should have reminded you yesterday, set your calculator to radian mode. Okay, and then Edson, can you find me the first endpoint value? Juliet, can you find me the second one? Either one of you when you're ready.
Is it 3.702?
Okay, Juliet, what do you have? I don't know, I'd like independent confirmation. If somebody else can just verify that Edson, you get the same thing as Edson.
I also got 3.702.
Okay. All right, that should make sense because secant is a close cousin to what other function? Like what did you use actually on your calculator? You used cosine. You probably typed in 2 over cosine of blank, okay? And cosine has the property of being an even function. An even function means cosine looks like this, and then it has mirrors itself on either side. So it should make sense that the value at -1 would mirror the value at +1. So that should be sensical to us. So those are the values of our endpoints. Now let's check our critical points. In order to check our critical points, we're gonna need the derivative. So we're gonna need dy dt with respect to t. So we want the derivative of 2 secant t, which is 2 secant t tangent t. And we wanna set that equal to 0. And we want to set that equal to 1 over 0 within the parameter that we've been given. In order to do this with our calculators, we're actually going to go back and graph it in Cartesian mode. It's the easiest way to check that. So switch your mode back and temporarily graph this in Cartesian mode. So you'll have 2. It's easier for us to solve. So we're going to graph that and then set your window from -1 to +1, but you should still be in radian mode. And what we're looking for zeros if there are any in that window, and we're looking for asymptotes if there are any in that window, because both of those count as critical points. All right, so we get 1 critical point of time being 0. Now you want to check the parameter, go back to parametric mode, and we want to check what the y value at 0 is. Okay, just like we checked the y value at -1 and +1, the endpoints, we're checking the y value at 0 also. Caitlin, can you get that one for me? And we're going to compare it to the other two.
Sorry, what am I doing?
Finding, now that we know the critical point is 0, we want to find the y value that goes with that. You probably don't need a calculator, shouldn't need a calculator to do this one, because you should be able to do 2 of the secant of 0 without a calculator. Okay. All right, and that is the only, since it's the only other critical point, then that has to be the lowest point for our parametric curve. And so at t equals 0, the lowest point is, and then we want to answer with both the x and the y coordinates. So we know that the lowest y coordinate is 2, and then we take time 0, we plug it into the x coordinate as well, and we get 0, 2. Yeah, so as we compared these relative y values, we compared that y value to the 2 y values that we got on the end point, and then this one is clearly the min, and there is no other candidate for the min because there are no other critical points. We've exhausted them all. We've checked all the endpoints. We've checked the only critical point, so that one has to be the min. So the minimum value we know for y is 2. We find the corresponding x value at the time of 0. Okay, let's try another one. This is a very similar question. Find the rightmost point for the parametric curve. So let's translate that as we think about optimization. If we want the rightmost point, what does that mean in optimization thinking? Jonathan, what do you think?
It's only about the x.
Okay, we're only thinking about the x, and which kind of x do we want? If we're
Maximum.
the maximum. Okay, very good. So we are trying to find the maximum x value. But our procedure is the same. We're going to check the endpoints and we're going to check our critical points and find which one is the maximum. So we check our endpoints and we're only checking it in x. So we want x to be equal to tangent of -1 and the other x to be equal to the tangent of +1. All right, so let's evaluate that. Alex, can you get me the tangent of -1? And Rain, can you get me the tangent of +1?
Tangent of positive 1 is 1.557.
Okay. That should also make sense to us because tangent is an odd graph which has symmetry in opposite quadrants, and so plugging in opposite values would yield opposite results. So those are my endpoints. So far, the maximum endpoint or the maximum value is happening at 1. So far. But now let's see if there are any critical points that might be more maximum than that. So we'll check that out. And so then we need dx dt. So we're taking the derivative. So secant squared of t. And we want to set that both equal to 0. And we want to set it equal to undefined. And we want to solve that within our parameter from -1 to 1. Okay, so now switch back to function mode, and you can solve this by graphing. And again, you're looking in the window of -1 to 1, and you're graphing the graph of secant squared, which would be 1 over the square of cosine, and you want to find out when that's equal to 0 and when it's equal if it does have any asymptotes or broken points of discontinuity. Okay, does it ever cross the x-axis in that window? No. Is it broken or have any asymptotes or discontinuities? No. So there are no additional critical points. So we've exhausted all the possibilities. We've checked the endpoints. We've checked for additional critical points, which there aren't any. And so then we're able to identify the maximum. So the maximum is happening right there. But we want to make sure we answer the question. And so the question would be, at time equals 1, the rightmost point is, and then we have 1.577, and then we want the y value to go with that so that we're answering the point. Bless you. I think we had that from the page before, that we knew that the value was 3.702, if I'm remembering that right. And so now we have the rightmost point of this graph was actually at the end point. Okay, any questions on that so far? All right, great. Okay, so let's take a little look at a little bit of a different curve. Here's a curve that is defined in X as a parabola, but is defined in Y as a trig graph. So we have the combination of a parabola graph and a trig graph. The graph is sketched for you here. You can see the initial point, according to the arrows, the initial point must be here. Okay, that is the initial. And the terminal point must be at the end over here, based on how we're following our arrows. So I've already done part A for you. Sketch a graph of the curve and indicate the direction in which it is traced. So I already have that. Now the part B, find the highest point on the curve and justify your answer. And so just even eyeballing it, it looks to me like the highest point of the curve is going to be somewhere where I have a horizontal tangent right in here. So maybe I'm eyeballing it right there. So it looks to me like a reasonable answer would be somewhere in the ballpark of about -3-ish. So let's actually check. We don't want to guess, but let's actually find the highest point. So go to the next slide. I've given you some space to work. So if we're going to do the highest point, we want to find the maximum y. The endpoints we already know are not going to be the highest just by looking at it. But if you didn't have the advantage of a graph, you would have to check the endpoints. So I'm just going to put that here. Check the endpoints, and we already can tell from the graph that the endpoints are negative, what was it, 5, 0, and positive 5, 0. So those were my endpoints. And then we want to check our critical point. So we just focus on just on the y. And so we want to look at dy dt, and the derivative of that would be 2 cos t. I'm going to set that equal to 0 and undefined. And I can solve 2 cos t equals 0 without needing anything additional. I know when cosine is equal to 0. So my cosine is equal to 0 at what times? You guys tell me. Okay, half pi is one of them. When else? Okay. I don't need to write and 3 pi over 2. And those are both of those in the parameter, in the time value that we've been given? Okay, no, this one's not. So it's only pi over 2, that's a possibility. So then we're going to check that and check what its y value, or x and y value would be. And so when I plug in pi halves into that, I'm going to get x equals pi halves for the time minus 5, squared minus 5, and the y would be 2 sine pi halves. So the y is going to be 2. Okay, Christian, can you quick do pi halves squared minus 5?
Yeah. Negative 2.533.
All right, and so that is our point. Our highest point is negative 2.533, comma 2. So we have our x value and we have our y value. All right, to find our inflection point, we're going to need to find the second derivative. All right, Jonathan, can you find the first derivative, please?
Negative 2 cosine t over 2t.
Okay, so is it negative or are you changing your mind?
No, it's positive.
All right, so positive 2 cos t over, what'd you say the denominator was?
2t.
Okay, so if we simplify that, we get cos t over regular t. Okay, good. All right, and to find our second derivative, we're going to need to apply the quotient rule to that, and it's still going to be over the same original denominator, so still over 2t. So the 2t is consistent as a denominator, but our numerator is now the derivative of the cosine t over t using the quotient rule. So that would be t times negative sine t minus cosine t times 1 all over t squared. So when we simplify this, I'm going to have negative t sine t minus cosine t, and my denominator becomes 2t cubed when I consolidate my denominators together. To find the inflection points, we're going to set this equal to 0, and we're going to set it equal to 1 over 0, which means using our calculators, switch back into function mode, and just use x as a graph and make sure you set your parameter up to 0 to pi. So this is just a way we use the graph in Cartesian mode, just to, it's easier for the calculator to graph it. So graph negative x sine x minus cosine x over quantity 2x cubed. Set your window to 0 to pi this time, and then look for any either zeros or points of discontinuity. All right, so the only solution we got from that was that 2.798 is a candidate. Now, is there actually a change there, Rain? If you look at that graph.
Or it's just straight, so
Yeah, slightly.
Slightly, okay?
I'm blind.
That's okay. I mean, you can trace it. You can trace it and watch the values on your graph and see if they, when you cross that, if they change from negative to positive. So you can just hit trace to do it. You can check a table. You can check the table values, or you can plug in. Yeah? So it's changing from what to what?
Negative to positive.
Okay. So it doesn't matter that it's changing from negative to positive, it just matters that it does change, right? So we do have our inflection point. Now, does that answer the question about what the point actually is? Okay, store that value in your calculator so that when you switch back to parametric, so that you can actually find that value. Okay, so store, save it as an A, or I don't care what you save it as alpha A. And then let's check what the x value is. So we want to take that value and plug it back into 2.798 quantity squared minus 5. And plug that value into 2 sine 2.798 so that we can, if you store that value, you'll get more accuracy. All right, Kaylin, do you have the x value yet?
2.831.
Anybody confirm that? Okay. All right, Edson, do you have the y value? Okay, anybody confirm that? Great. All right, so that's our inflection point. All right, any questions about optimization before we move on to length of curve? All right, so let's do length of curve. All right, so here is the version of the length of the curve equation that has respect to t. So if you want to, I mean, we already wrote it down, but the one we were working on before was a to b square root of dx over dx quantity squared plus dy over dx quantity squared, and then with respect to the differential dx. This time it's just over t with respect to t, and our times are our parameters time 1 and time 2. So this is how we measure the length of a curve in a parametric sense. So I think we're ready to just apply that. Hopefully that makes sense to you. It connects to what we did before, and we can find the length of a curve defined by this equation. All right, so L equals, my integral is going to match the parameter. So the parameter would be 0 to 2 pi. The square root then would have the derivative of x with respect to t. So that would be cosine t, quantity squared. And then the derivative of y with respect to t, which would be negative sine t, quantity squared. And then that is dt. Okay, now go ahead and switch back to function mode and run this as a Math 9. So you'll run the integral from 0 to 2 pi of the square root function. Make sure you put parentheses around the negative so that we don't mess that up. And then as soon as anybody has that, they can let me know. $6.283. Can I get confirmation on that from anybody? Okay. Does that number ring a bell? Okay. If pi is 3.14159, then this is 2 pi. Okay. Now, let's see if what does the shape of this look like? It's a circle. And the length of a circle is also known as what word? The length, the circumference. And what's the formula for the circumference of a circle? 2 pi times whatever the radius is. And what's the radius of this circle is 1. And so this proves the formula for the circumference of a circle. Okay, any circle will work out that way. Okay, one more. This one is not a circle. Okay, find the length of the parametric curve. So let's take a look at the picture a minute. So switch to parametric mode and go ahead and let's get a look at the graph so that we can understand what we're measuring here before we find the length. Set your parameter to 0 to 2 pi. I'm going to come around and take a look. So you're going to pick a graph like this. So we're finding the length.
I gotta leave. I have a soccer game I have to head up to.
Bye, good luck. So I'll give you a way to help your calculator out. All these segments are all the same, aren't they?
Yeah.
So if you could find one of them, and you just multiply it by 4. So that would be easier on your calculator. If instead of going 0 to 2 pi, if you went 0 to pi halves and just did one of the sections, your calculator doesn't have to work quite as hard, and then multiply that by 4. So then the square root would be the derivative. So 3 cosine t quantity squared times the chain rule, all that squared, plus 3 times sine t squared times the chain rule on that, cosine t, and all that squared. So be careful you use the chain rule too, and then dt. So your calculator's working really hard anyway, so you might as well make it a little easier on the calculator by changing the values.